If I multiply 3 factors of 2, I get 8, right? And then what I can do is write this 2 as a base of my logarithm, and the result, which is number 8 here. And turns out logarithm is nothing else but the power I have to raise my base to produce that result. In other words, if I have another logarithm and wonder what power I have to raise 3 to produce number 9, then the power will be 2. So the result is 2. You see how we can rewrite these logarithms just like powers. So let's do one more. Logarithm of base 2 taken of number 0. What power I have to raise 2 to produce 1? Well, looks like the power has to be 0, right? So 2 to the power of 0 is 1. Again, the logarithm is nothing else but the power. And that's pretty much all we need to realize when we do the exercises related to the logarithms. Because all we use is powers. But yes, we write them in a little bit unusual way. Turns out this way is popular for some particular exercises, and that's why we need to be familiar with these logarithms. So other thing they're talking about here is a bunch of properties of logarithms that I hope you encountered in the previous class in the college algebra. If not, it's fine. I will go over some of them. But the idea is that you can actually use the couple of logarithms in a calculator. So it turns out the logarithm of base 10 taken of number x, you can write as just log of x. And they call it as a common logarithm. So there are some exercises that you will encounter. And the other one that deal with number e. Number e, remember, was 2.71, something we already encountered in the previous section. We even took derivatives of e to the power of x. So when you have a logarithm with such a base as e, then this is ln. So they put this ln of x, and that's what you're gonna also see in this textbook. In fact, I think the whole point of this story is dealing with that ln. And that's actually what we have here, the definition of ln, which is logarithm base e. So other part of this is talking about taking a derivative of that ln, and actually derivative of ln is equal to 1 over x. So that's the part that we have in calculus. So if you saw logarithms before, you definitely didn't see the formula for its derivative. And that's what I'd like to use today. So we are going to get used to this formula, as well as we're going to, well, look at some of the properties of logarithms along with that. So let me try to do exercise, let's say problem number 11, that says, write this equation that contains logarithms using powers. So in exercise 11 in section 3.2, where we have 10 to the second power, which is equal to 100, what I can do is write this as a logarithm of base 10. Let's see, why base 10? Well, that's a base of my power, right? And this logarithm will be equal to number 2, because the logarithm is nothing else but the powers. So this power of 2 is what I have equal to the logarithm. And the result of this squaring of 10 is 100. So the result we put here. I say, Alex, you could just say it's log of 100 equal to 2 because you just said the base 10, you don't write because of this definition of so-called common logarithm. When I say, what if I write base 10? Well, that's fine, I will understand, but I guess we don't write it. And that's the idea. So I just manipulating with various powers, and looks like there is a bunch of exercises that deal with the plug-in numbers in a calculator. So you could just plug all of these into the calculator. Let me try problem number 25. So those are basically calculator exercises. So if I find my favorite scientific calculator and put ln of 5/4 in it, then you can just go for that favorite Decimus, right? Oh, actually, we used to go scientific calculator. And the choice 1 was that Decimus, right? So I put in it ln. So when you say, how do you put ln? I don't see it here. Well, you need to go to the functions. So you need to click on that menu and you will see the choice, which is called ln, or sometimes it will say natural logarithm. So once you hit that ln, then you need to enter 5/4, and to do that, you need to return back to the main menu where the numbers are, where we actually started this exercise. So I put 5 on the top, and then 4 on the bottom as usual, and get whatever number it is. So I guess this is a pure calculator exercise. So it's good to be aware that ln is what you can take by the calculator, but not the logarithms of various other bases, like base 2 of 8 or something. So ln is what we can deal with. And let me go back to these exercises and see they're actually talking about these problems here in the section. So how about if I try to differentiate? How about if I try exercise number 49 here? So I'm gonna be looking at the 49 that says find the derivative or differentiate. Those are the same words, right? See, so why do they call it differently? Well, historically, I guess, but it's actually important to realize it's the same. So when I'm looking for the derivative of this, so -8 is multiplied by the derivative of ln, and new formula comes into play. So you multiply -8 by 1/x, just like that. So with ln, we have this type of a story. So let me try to differentiate one more. Let's say, how about problem number 52? Find the derivative of that. Well, let us write this x to the power of 6, right? Multiplied by ln of x. And this is a quarter that I subtract, multiplied by x to the power of 4. So there is a little problem here. We have a product. Do you see that x to the power of 6 is actually multiplied by what we have, so ln x. So we are to use the f times G structure, and its derivative, which is F prime G plus G prime F, right? I better write it carefully. So we're to prepare these pieces, such as a function F that is x to the 6, function G, which is ln, right? Then we need to take their derivatives. Well, it wouldn't be hard to take derivatives of these pieces. They're nice. So first one will be 6 on the ground and x power of 1 less, 5. You still remember that? So we subtract 1 from the power, right? And then derivative of ln, which is 1 over x. So let us set up this sum of pieces. So instead of f prime, I put 6x power of 5. Then I multiply this by g, which is multiplying by ln of x, right? And then we're gonna add this with, now I have to take a g prime, which is 1 over x, right? 1 over x. And then times this by function g, which is ln of x. Now I need to take care of derivative of the other piece. So minus 1/4 is gonna stay. And then 4's power of x. So I have 4, and then x will be raised to the power of 3. So we just did some algebra. We can also cancel these 4's, but that's all it is. So it looks like we added one more formula to our list of formulas, and it is good to be familiar with those formulas. And of course, we just want to make sure that you feel comfortable when you see ln and just take its derivative without any panic, because it's just a little special formula with it. How about exercise number 63? That has not a very nice looking structure, right? So what I can do when I take its derivative is to prepare. What I'm gonna do is notice that I can divide this x squared and minus 7 by x separately, because I don't like quotients. Remember, we always want to take derivatives of powers of x. And notice I was able to write this as a power. So I will write this as a ln of x minus 7 raised to the power of negative first. And this way, I'm gonna take a derivative, and taking that derivative this way, I will avoid using the sister formula for, remember that f prime g and g prime f, and then there's a denominator on the top of it. Who needs it? If you can find the other way, then always use it. So I have a function ln. So the derivative will make ln to go away, but put 1 over whatever's logarithm applied for. So that'd be x minus 7x raised to the power of minus 1. And then I have to times this by derivative of my parentheses. So inside the parentheses, I'm going to have 1 in here. And then negative 7 will also be multiplied by the power. Remember, now we have a power rule. So the power of x is negative 1. So I'm going to have a minus 1 in front on the ground. And it's raised, that x is raised to the power of negative 2. So this is my chain rule in here. So it's quite messy, and some people may feel like simplifying. It's always a good feeling if you feel like simplifying, but if you don't feel comfortable, you don't have to, because they ask you to differentiate. So you did. So I could just write this as 1 over x minus 7 over x. I'm going to simplify, and you will see that it's not really going to bring us to anything very nice looking. So that's my first piece times. Now, what's the second piece? Well, looks like this will be 1, and then minus and minus is plus, right? And then 7 is divided by x squared. Please notice that 1 as a numerator is not really needed. I could put that whole structure in numerator. But what really bothers people that we have this so-called complex fraction, right? See, I selected this exercise on purpose to show you how to simplify the complex fraction if you want to. So what I will do is multiply by that largest power of x, which is x squared, and my numerator by x squared, and my denominator by x squared. That doesn't change my fraction, but then I have to distribute this x squared here and here, as well as in my denominator, and this way I will get no complex fractions. So it is involved with very heavy algebra, looks like, this type of exercise. So what do we get on the top? Well, x squared will be multiplied by 1, so just x squared plus. Now notice that you're going to cancel your denominator, because you're going to have 7x squared divided by x squared. And that's actually why we do this. So x squares will cancel. On the bottom, we're going to have x to the power of 3 when we distribute. And then again, 7x squared, but x is still in denominator. So it's time to rid of those denominators, to cancel them and make life much easier. So here also cancel x squared, I just have x left. And then we get the answer. So it'll be x squared plus 7 in numerator, and x cubed minus what? 7 times x in denominator. So heavy algebraic manipulations. I think you should be able to see them, and if you need, you should be able to look at this recording and get a piece of paper, pen, and actually follow through this. But my goal is not to make you do this for the exercises. Remember, we just need to be familiar with derivatives and taking them, and then see how to use them in calculus, because this problem really leads us nowhere. We just take derivative and we just playing with these derivatives again and again. So I'll do one more, like exercise 72, that looks real unusual. So why don't I do it and stop with this? So 72 that has composition of functions. We're applying one ln to another ln of 3x in the parentheses. So when you take a derivative of this entire structure, then you're going to have to put 1 over, right? 1 over what? Well, 1 over this ln in the parentheses, right? ln of 3x. That's first piece. But we have a chain rule. So once we took care of the ln on the outside, now I go with the derivative of that ln inside the parentheses, and that's again 1 over, and now I have 3x to put in the bottom. You see that? And then finally, we need to get inside of those innermost parentheses, so that's 3x. So I take derivative of 3x and I get 3. You see how the answer looks like? I say, Alex, answer is going to look even better if you cancel 3, and I can write it again. So we're going to have just 1 in my numerator, and then there'll be x left, which is multiplied by ln of 3x. So notice I can put x in front. I can always commute those factors, and that way we get, well, I guess a little bit nicer looking answer. But again, you can take derivatives of just about anything. So how about if you take a little derivative using the formula that we just started to get used to, derivative of ln, which is 1 over x. Let me do problem 53, and you can try 54, which is very, very similar, just a little different number. 53 has ln of 6x. So let me try to find the derivative of this ln of 6x. And to do this, I'm going to utilize the formula. So I'm going to write it as 1 over just 6x, right? So ln is gone, and whatever we applied ln to is now in denominator. And now I need to multiply it by derivative of 6x, which is actually number 6, right? So here's our answer. 1 is on the top and x is on the bottom. 6 and 6 nicely cancel. So we have the result. So a little quiz for today. Exercise number 54. I hope you're going to like it. Very, very similar to the problem I just done for you. So quiz is again uses the same exact formula.